Hey there, how's it going? Thanks for joining me today. Whether you're relaxing at home, on your commute, or winding down for the evening, I'm really glad you're here. Picture this. It's October 15th, 2024, 11:43 p.m. Hawaiian time. While most of the world sleeps, Dr. Sarah Chen sits alone at her monitor in the Atlas facility on Mauna Loa, running what she assumes will be another routine asteroid detection sweep. The system flags an anomaly, a fuzzy patch where yesterday there was nothing. Within minutes, she realizes this isn't just another space rock drifting through the cosmic void. This is Comet C/2024 S1, soon to be known simply as Atlas. And something about its motion makes her hands shake as she types the alert that will change everything. Before we continue this journey, tell us where you're tuning in from, and if this story resonates with you, make sure you're subscribed, because tomorrow I've saved something extraordinary for you. Now, to properly appreciate what Dr. Chen discovered. That night, we need to understand exactly what she was looking at. Atlas measures 2.1 kilometers across. If you're having trouble visualizing this, imagine 7 Empire State Buildings lined up end to end. This cosmic mountain travels at 67 kilometers per second, fast enough to circle our entire planet in 10 minutes. These numbers are, one must admit, rather difficult to wrap one's head around. But here's what turned Chen's blood cold, what made her triple-check her calculations with the obsessive precision of someone who desperately wants to be wrong. The trajectory showed a curve that shouldn't exist. Comets, you see, follow predictable paths. They're cosmic clockwork, governed by the same gravitational laws that keep your coffee mug from floating away from your table. Except this one had changed course. And comets, as a general rule, don't just decide to take scenic detours. The moment of realization must have been extraordinary. Picture Chen staring at her screen, watching numbers that represent the difference between a spectacular light show and the end of civilization as we know it. She's looking at data that suggests a 2-kilometer mountain of ice and rock, roughly the size of a small city, has somehow altered its trajectory toward Earth. The absurdity of the situation would be almost comical if it weren't absolutely terrifying. Chen doesn't panic, because panic isn't particularly useful when you're possibly looking at humanity's extinction event. Instead, she does what astronomers do. She checks her math. Then she checks it again. Then she calls her colleagues at other observatories, using the kind of carefully neutral tone that suggests either complete confidence or complete terror. In this case, it was definitely the latter. The waiting begins immediately. Chen sends her preliminary observations to the Minor Planet Center in Massachusetts, the global clearinghouse for asteroid and comet discoveries. But preliminary observations, however alarming, aren't enough to trigger the end-of-the-world protocols. For that, you need confirmation. And confirmation means waiting 17 hours for other telescopes to verify that, yes, indeed, a mountain-sized chunk of ice and rock appears to be heading directly toward the only known planet with decent coffee shops. During those 17 hours, Chen experiences what can only be described as the longest night shift in human history. She keeps watching Atlas through her telescope, taking measurement after measurement, hoping each new data point will reveal some error, some miscalculation that transforms cosmic catastrophe back into routine space debris. The measurements remain stubbornly consistent. Atlas continues its impossible curve toward Earth. The confirmation arrives from the Catalina Sky Survey in Arizona at 4:17 p.m. the following day. Dr. Eric Christensen, who has discovered more asteroids than most people have had hot dinners, reviews Chen's data and runs his own observations. His initial response, according to leaked recordings, consists of approximately 30 seconds of creative profanity, followed by the professional observation that this can't be right. Unfortunately, it is right. Atlas has indeed changed course, bending its trajectory from a harmless pass through the outer solar system to a collision course with Earth. At this point, The story becomes a study in how institutions respond when faced with the impossible. The Catalina team contacts NASA's Jet Propulsion Laboratory. JPL contacts the Planetary Defense Coordination Office. The PDCO contacts the European Space Agency, which contacts observatories worldwide. Within 6 hours, every major telescope on Earth capable of tracking near-Earth objects has swiveled toward Atlas like a collection of very expensive, very worried eyes. The human drama unfolding behind these institutional responses deserves particular attention. Chen, thrust suddenly into the role of harbinger of potential apocalypse, finds herself fielding calls from astronomers she's only read about in journals. Her estranged daughter calls after seeing her mother's name trending on social media. Apparently, astronomer discovers extinction-level comet generates considerable online discussion. The facility janitor, a retired teacher named Miguel Santos, brings Chen coffee and stays to witness history being written in real time. Dr. Patricia Williams, the professor who taught Chen orbital mechanics 20 years earlier, drives 4 hours from the University of Hawaii to help verify calculations that nobody wants to believe. Meanwhile, Atlas continues its serene journey through space, completely indifferent to the growing panic it has inspired. This indifference represents one of the more unsettling aspects of cosmic threats: their utter lack of malice or intent. Atlas isn't angry at humanity. It hasn't developed grudges against Earth's inhabitants. It's simply following the laws of physics with the reliable consistency of a cosmic bureaucrat. The fact that these laws happen to dictate a collision course with our planet is, from the universe's perspective, merely an interesting coincidence. The numbers tell an increasingly grim story. Atlas orbits the Sun every 4.7 years, a relatively short period that suggests an origin in the inner regions of the asteroid belt. Its composition, approximately 60% water ice, 20% carbon dioxide ice, and 20% rocky material, marks it as a typical comet, albeit an unusually large one. The 17-degree inclination of its orbit relative to the plane of the solar system initially made detection challenging, like spotting a car approaching from an unexpected angle on a cosmic highway. What makes Atlas particularly troublesome isn't just its size or composition, but its velocity. At 67 kilometers per second, it carries kinetic energy roughly equivalent to 10 million megatons of TNT. For comparison, the largest nuclear weapon ever detonated, the Soviet Union's Tsar Bomba, yielded 50 megatons. Atlas carries the energy of 200,000 Tsar Bombas compressed into a single projectile. This is what physicists call a significant amount of energy, though they typically use more technical language when discussing the potential obliteration of their home planet. As word spreads through the astronomical community, a curious phenomenon occurs. Scientists who spend their careers studying distant galaxies and abstract mathematical models suddenly find themselves contemplating very immediate, very practical questions. How long would it take to evacuate major population centers? Which underground facilities could serve as shelters? How many seeds could fit in secure storage? These questions represent a rather jarring shift from theoretical astrophysics to applied survival planning. The psychological impact on the Discovery team becomes apparent in interviews conducted months later. Chen describes a persistent sense of unreality, as though she were watching someone else's life unfold on television. The magnitude of the discovery that she, of all people, had spotted humanity's potential extinction event creates a cognitive dissonance that human brains struggle to process. It's rather like discovering that your morning jog has accidentally led you to the edge of a cliff, except the cliff is moving toward you at cosmic speeds. Dr. Christensen, whose confirmation elevated Chen's discovery from possible error to probable catastrophe, later admits to calling his wife and suggesting they take that European vacation they'd been postponing. Not because he knew the world would end, but because the possibility suddenly made delayed gratification seem like a questionable strategy. This response, the urge to accelerate life experiences in the face of cosmic uncertainty, becomes increasingly common as news of Atlas spreads. The international response begins with carefully worded communications between space agencies. Nobody wants to be the first to use the phrase extinction-level event in an official document, though everyone understands that's precisely what they're discussing. The language becomes increasingly bureaucratic as the implications become increasingly dire. Significant kinetic impactor with high Earth intersection probability sounds much more manageable than giant rock that might kill everyone. Meanwhile, Atlas continues its approach with the punctuality of a cosmic train. Its position updates arrive like clockwork, 17 astronomical units from the Sun, then 16.9, then 16.8. Each measurement narrows the error bars on its trajectory calculations. Each calculation makes the probability of impact slightly more certain. By October 18th, 72 hours after Chen's initial discovery, the mathematics have become uncomfortably clear. The decision to inform the public requires careful consideration. Government officials, space agency administrators, and crisis management experts engage in the delicate process of determining how to announce that humanity faces potential extinction without triggering mass panic, economic collapse, or widespread social breakdown. This proves to be a remarkably complex communication challenge. Rather like trying to mention that the building might be on fire without causing anyone to rush toward the exits. The announcement, when it finally comes at 11 p.m. Eastern Time on October 18th, represents a masterpiece of bureaucratic understatement. The official statement describes Atlas as a near-Earth object, requiring enhanced monitoring and preliminary assessment of deflection options. This phrasing manages to simultaneously acknowledge the threat and minimize its psychological impact. Though anyone capable of basic translation from government speak to plain English quickly grasps the essential message, we might all be in considerable trouble. The global response to this announcement provides fascinating insight into human nature when confronted with cosmic-scale problems. Some people immediately begin hoarding supplies, as though canned goods might prove useful in the event of planetary sterilization. Others book expensive vacations, reasoning that potential extinction makes credit card debt irrelevant. A surprising number simply continue their normal routines, displaying the remarkable human capacity to normalize even the most abnormal circumstances. Chen, meanwhile, finds herself transformed overnight from unknown astronomer to reluctant spokesperson for humanity's cosmic predicament. Interview requests flood her email. News crews arrive at the Atlas facility. The woman who discovered the end of the world becomes rather improbably a minor celebrity. She handles the attention with the bemused grace of someone who never expected to become famous for potentially doom-related reasons. The story of Atlas's discovery reveals something profound about the intersection of individual moments and cosmic events. Chen's decision to work late that Tuesday night, the routine software scan that flagged an anomaly, the 17 hours of verification, these small human actions suddenly carry the weight of species survival. It's the kind of cosmic coincidence that makes you wonder about the universe's sense of timing and whether it might benefit from a few lessons in dramatic pacing. As October draws to a close and Atlas continues its approach, humanity faces an unprecedented challenge. How do you prepare for something that might not happen but absolutely could? The answer, as we'll discover, involves nuclear weapons, international cooperation, and the kind of desperate ingenuity that only emerges when extinction provides motivation. But that's a story for tomorrow. For now, we're left with Dr. Sarah Chen, sitting in her Hawaiian observatory, watching a mountain of ice and rock that may or may not be heading toward the end of everything we've ever known. In the grand scheme of cosmic events, it's just another comet following the laws of physics. In the somewhat more limited scheme of human survival, it's the beginning of the most important race our species has ever run, and we have exactly 237 days to win it. To understand how Atlas became humanity's potential nemesis, we need to travel back in time, not just a few years, but 4.5 billion years, to when our solar system was little more than a swirling disk of gas and dust surrounding a newborn star. This was a chaotic time, cosmically speaking. Imagine the universe's most violent construction project, with planets forming through a process that can only be described as aggressive accretion. In this primordial maelstrom, countless chunks of ice and rock began their eternal dance around the sun. Atlas was one of these, a modest clump of frozen water, carbon dioxide, and rocky debris that would have seemed utterly unremarkable to any hypothetical observer. Of course, there were no observers at the time, which was probably for the best, as the early solar system was not what you'd call a hospitable place for tourism. Most of these icy bodies ended up in what astronomers call the Oort cloud, a spherical shell of frozen objects extending roughly 1 light-year from the sun. To put this distance in perspective, if the sun were the size of a basketball sitting in the center of a major city, the Oort cloud would extend past the suburbs, through the countryside, and well into the next state. It's really quite remarkably far away, which explains why comets from this region take millennia to complete their journeys to the inner solar system. For 4.5 billion years, Atlas slept in these frozen depths, a kilometer-wide time capsule preserving materials from the solar system's birth. This is where the story becomes particularly fascinating from a physics perspective, because Atlas wasn't just sitting there doing nothing. It was slowly, imperceptibly, beginning the chain of gravitational encounters that would eventually point it toward Earth. The universe, it turns out, has a very long memory and an apparently twisted sense of humor. The first significant event in Atlas's transformation from harmless iceball to potential civilization ender occurred 70,000 years ago. This was when Schultz's star, a red dwarf roughly 20 light-years from our solar system, decided to take what amounted to a cosmic stroll through our neighborhood. Now, when astronomers say a star passed through the Oort cloud, they don't mean it actually hit anything. Space is, as Douglas Adams noted, big, really big. But gravitationally speaking, Schultz's star was like a bowling ball rolling through. A room full of ping-pong balls, suspended on strings. The gravitational interaction was gentle by cosmic standards, roughly equivalent to someone nudging a marble with a feather. But when you're dealing with objects that have been sitting motionless for billions of years, even a feather nudge can set remarkable things in motion. Atlas, along with thousands of its icy neighbors, received a tiny gravitational push that began its long fall toward the inner solar system. This journey inward took 70,000 years, which gives you some sense of the scale we're dealing with. If you had started timing Atlas's approach when the first modern humans were painting caves in France, you would still be waiting for it to arrive. The comet moved with the patient persistence of geological time, slowly picking up speed as the sun's gravity pulled it inward. But here's where the story becomes truly interesting from a celestial mechanics perspective. Atlas wasn't just falling straight toward the sun like a dropped stone. It was following what mathematicians call a hyperbolic trajectory, a path that would carry it past the sun and back out into deep space, never to return. Under normal circumstances, Atlas would have put on a spectacular show for astronomers sometime in the summer of 2025, then disappeared forever into the cosmic dark. September 2023 changed everything. This was when Atlas encountered Jupiter, the solar system's gravitational bully, at a distance of just 27 million kilometers. In astronomical terms, this qualifies as uncomfortably close, roughly equivalent to 2 cars passing each other on a cosmic highway with only a few meters to spare. Jupiter, being roughly 318 times more massive than Earth, doesn't ask politely when it wants to alter a comet's trajectory. Its gravity grabbed Atlas like an invisible hand, bending the comet's path by 7.3 degrees. This might not sound like much, but when you're dealing with objects moving at interplanetary speeds across astronomical distances, small angular changes produce enormous differences in destination. The mathematics of this gravitational encounter are elegantly beautiful and utterly terrifying. Jupiter's influence transformed Atlas from a harmless visitor into a guided missile aimed at Earth, the planet that has historically protected us from cosmic impacts by sweeping up dangerous debris had, in this case, performed the opposite function with devastating precision. But Jupiter's gravitational nudge was only part of the story. As Atlas swung past the giant planet and began its journey toward the inner solar system, solar radiation started warming its icy surface. This is where comets begin their transformation from invisible chunks of frozen matter into the spectacular, tailed objects that have inspired human wonder and terror. Throughout history, the warming process creates what astronomers call outgassing. Jets of vaporized ice and dust shooting from the comet's surface as frozen materials sublimate directly into space. Under normal circumstances, this outgassing creates the beautiful coma and tail that make comets such magnificent celestial objects. In Atlas's case, it also created tiny rocket engines randomly firing across its surface. This is where the Yarkowski effect comes into play. Named after Ivan Yarkowski, a Polish civil engineer who, in 1896, had the rather remarkable insight that sunlight could actually push objects around in space. The effect is subtle, the equivalent of a gentle breeze pushing against a massive ship. But when that ship is traveling across millions of kilometers of empty space, even a gentle breeze can dramatically alter its final destination. Atlas spins unevenly as it tumbles through space, which means the jets of vapor don't fire symmetrically. Some push the comet in one direction, others push it in another. The net effect is like having a spacecraft with randomly firing thrusters that nobody can control. Each jet adds or subtracts tiny amounts of velocity, and these tiny changes compound over the millions of kilometers between Jupiter and Earth. The combination of Jupiter's gravitational deflection and the asymmetric outgassing created a perfect storm of orbital mechanics. What should have been a predictable, harmless pass through the inner solar system became something far more sinister. By the time Earth's astronomers spotted Atlas in October 2024, it had transformed from tourist to assassin. To understand how unlikely this sequence of events actually was, consider the precision required. Jupiter had to be in exactly the right position when Atlas arrived. The comet had to approach from exactly the right angle. The asymmetric jets had to fire in exactly the right pattern. Change any one of these variables by even a small amount, and Atlas would have sailed harmlessly past Earth, providing a spectacular light show before disappearing back into the depths of space. The odds against this particular combination of events are approximately 1 in 14 million. To put this in perspective, you're roughly 7 times more likely to be struck by lightning while being attacked by a shark during a solar eclipse. The universe, it seems, occasionally enjoys demonstrating its capacity for malicious coincidence. These cosmic billiard ball mechanics work through principles that are both elegant and merciless. Imagine rolling a bowling ball past a powerful magnet, while someone randomly pushes it sideways with varying force. Each influence seems minor in isolation, but combined over enormous distances, they can spell the difference between a near miss and catastrophic impact. The universe operates like an impossibly complex pinball machine, and we had just watched the ball head straight for the bumper marked Earth. The discovery of Atlas's altered trajectory also revealed something profound about our solar system's hidden dynamics. For centuries, astronomers have mapped the predictable movements of planets and moons, creating the impression of a cosmic clockwork operating with reliable precision. Daedalus reminded us that chaos lurks within this apparent order, that gravitational interactions across vast distances and timescales can produce outcomes that nobody anticipated. The scientific community's initial response to these orbital calculations combined professional fascination with personal dread. Dr. Alan Harris at the Space Science Institute described reviewing the trajectory analysis as watching mathematics transform from abstract beauty into existential threat. The same equations that normally describe elegant celestial dances suddenly spelled out humanity's potential extinction with mathematical certainty. What made Atlas particularly troubling wasn't just its size or speed, but its stealth approach. The 17-degree orbital inclination that resulted from its encounter with Jupiter meant it was approaching from an angle that made early detection difficult. Most near-Earth object surveys focus on the ecliptic plane, where most asteroids and comets travel. Atlas was coming from cosmic left field, literally and figuratively. The comet's composition added another layer of complexity to the threat assessment. The 60% water ice content meant that Atlas would likely survive atmospheric entry largely intact, rather than breaking apart into smaller pieces. While a fragmented impact would spread destruction over a wider area, a single massive impact would concentrate all that kinetic energy into one devastating blow. Neither option qualified as good news, but the single impact scenario carried implications that kept atmospheric physicists awake at night. Perhaps most unsettling of all was the realization that Atlas represented just one example of cosmic roulette. The Oort cloud contains an estimated 2 trillion comets, any of which could theoretically follow a similar path under the right circumstances. The discovery forced humanity to confront an uncomfortable truth. We live in a cosmic shooting gallery, and we've been extraordinarily lucky for the past 65 million years. As Atlas continued its approach through the winter months of 2024, astronomers refined their understanding of its properties and trajectory. Each observation narrowed the uncertainty ranges, and each refinement made the mathematics more precise and more terrifying. The comet was behaving exactly as celestial mechanics predicted, following Newton's laws with the reliability of a cosmic metronome counting down to potential doomsday. The international astronomical community found itself in the unprecedented position of tracking humanity's possible extinction with scientific precision. Observatory schedules worldwide were reorganized around Atlas observations. Graduate students who had expected to spend their careers studying distant galaxies suddenly found themselves calculating impact probabilities and crater diameters. The abstract had become immediate, the theoretical had become personal, and the beautiful mathematics of orbital mechanics had revealed their capacity for cosmic malevolence. By February 2025, with Atlas now visible to amateur astronomers with modest telescopes, the comet had become both humanity's most studied celestial object and its most feared. The cosmic billiard ball that had begun its journey in the frozen depths beyond. Pluto was now close enough that its jets of outgassing vapor were visible as a faint coma surrounding its rocky core. In just 3 more months, we would discover whether 4.5 billion years of cosmic coincidence would culminate in humanity's greatest triumph or its final chapter. October 16th, 2024, 4:17 a.m. Eastern Time. The phone rings in the Washington office of NASA's Planetary Defense Coordination Office with the particular urgency that suggests someone, somewhere, has discovered something they desperately wish they hadn't. Lindley Johnson, who holds the rather unique distinction of being Earth's first and only official planetary defense officer, answers with the practiced calm of someone whose job description includes preventing cosmic apocalypse. The breathless report from Hawaii changes everything. Within an hour, telescopes worldwide begin swiveling toward Atlas like a collection of very expensive, very worried eyes. What follows is perhaps the most intense 72 hours in the history of astronomical observation, a period when humanity's best minds race against time to determine whether we're looking at a spectacular cosmic light show or the end of civilization as we know it. The initial response reveals something fascinating about how institutions behave when confronted with the impossible. NASA's Deep Space Network, normally occupied with monitoring distant spacecraft, suddenly redirects its attention to an object that's becoming decidedly less distant with each passing hour. The European Space Agency's optical ground station in Tenerife cancels routine observations to join the global vigil. Even amateur astronomers with backyard telescopes receive coordinates and urgent requests for confirmation photographs. This mobilization of Earth's astronomical resources represents humanity's first coordinated response to an extinction-level threat. The speed of the response is impressive. The underlying panic, carefully concealed beneath layers of scientific protocol, is palpable. When the world's most powerful telescopes simultaneously abandon their scheduled observations to stare at the same patch of sky, it tends to suggest that something rather significant is happening. The mathematics of uncertainty begin immediately. Each observation of Atlas produces what astronomers call an error ellipse, a region of space where the comet might be at any given moment. Initially, this ellipse is enormous, stretching across millions of kilometers. The goal is to shrink this uncertainty through repeated observations until the error bars become small enough to determine Atlas's exact trajectory. Unfortunately, some trajectories within the initial error ellipse pass uncomfortably close to Earth. Dr. Paul Chodas at NASA's Center for Near-Earth Object Studies finds himself in the unenviable position of calculating impact probabilities that he hopes will remain hypothetical. His initial assessment, based on the Hawaiian observations, suggests a 1 in 10 million chance of Earth impact. This sounds reassuringly remote until you realize that lottery tickets offer better odds, and people win those with disturbing regularity. The first 12 hours produce a steady stream of observations that gradually narrow the uncertainty. Telescopes in Chile capture Atlas during their nighttime hours. Australian observatories pick up the vigil as Earth rotates. The Catalina Sky Survey in Arizona, which confirmed Chen's initial discovery, continues taking measurements with the obsessive precision of astronomers who understand that tiny errors in measurement can translate to massive errors in predicting where a mountain-sized object will be in 7 months. By noon on October 16th, something troubling becomes apparent. Instead of the error bars shrinking to exclude Earth impact, they're shrinking around a trajectory that passes uncomfortably close to our planet. The impact probability climbs, 1 in a million, then 1 in 100,000. Each new observation should provide reassurance. Instead, it provides mounting dread. At 2:15 p.m. Eastern, the European Southern Observatory's Very Large Telescope in Chile, a facility with the refreshing honesty to admit that yes, it is indeed very large, produces measurements precise enough to eliminate most of the uncertainty ellipse. The remaining possibilities cluster around trajectories that bring Atlas within 50,000 kilometers of Earth. This is roughly twice the distance to geostationary satellites, which sounds like a comfortable margin, until you realize that comets don't follow flight paths as precisely as commercial aircraft. The impact probability reaches 1 in 10,000 at 4:37 p.m. This threshold triggers protocols that have existed in theory but never been tested in practice. Secure communications networks activate between space agencies, defense departments, and emergency management offices worldwide. The conversations that follow must rank among the more surreal diplomatic exchanges in human history. How, exactly, does one inform allied nations that a mountain from space might end civilization sometime next spring? The human drama behind these institutional responses deserves particular attention. Johnson, thrust into the role of coordinator for humanity's first potential extinction event, finds himself managing a crisis that no training program could adequately prepare anyone for. His office, designed for tracking routine asteroid passes, suddenly becomes the nerve center for what might be the most important scientific investigation in human history. The irony that Earth's planetary defense consists largely of one man with a phone and access to telescope networks is not lost on the participants. Meanwhile, astronomers worldwide experience the peculiar stress of hoping their calculations are wrong. Dr. Amy Mainzer at the University of Arizona, whose team specializes in thermal infrared observations of near-Earth objects, finds herself rechecking measurements with the desperate intensity of someone looking for mathematical salvation. Each new data point should clarify Atlas's trajectory. Instead, each measurement brings the potential impact zone closer to Earth's orbital path. The international response reveals fascinating differences in institutional cultures. The Japanese Space Agency responds with methodical precision, providing hourly observation updates formatted with bureaucratic clarity. The Russian space program contributes observations, along with what can only be described as fatalistic commentary about cosmic inevitability. The Chinese National Space Administration offers extensive telescope time while maintaining official silence about the implications of their measurements. October 17th brings the breakthrough everyone simultaneously wanted and feared. Dr. Mainzer's team at the University of Arizona completes their 17,430th observation of Atlas using thermal infrared imaging, a technique that measures heat radiation rather than reflected sunlight. This method provides extraordinarily precise measurements of the comet's position and velocity, eliminating most remaining uncertainty about its trajectory. The result stops conversations mid-sentence across observatories worldwide. Impact probability has jumped to 1 in 3. The error ellipse has shrunk to a narrow band that passes directly through Earth's orbital path. Atlas isn't definitely going to hit Earth, but it's no longer definitely going to miss. The mathematics have transformed from reassuring to terrifying in the space of a single observation. The moment when this calculation appears on screens in Arizona represents one of the more profound instances of human discovery. Unlike the excitement that typically accompanies astronomical breakthroughs, this moment carries only dread. Mainzer later describes the experience as watching. Mathematics evolved from abstract beauty into existential threat. The numbers on her screen represent the difference between Atlas becoming a spectacular comet visible to amateur astronomers and Atlas becoming the object that ends human civilization. The reaction in observatories worldwide follows a predictable pattern: stunned silence, followed by frantic recalculation, followed by the gradual acceptance that the mathematics are correct. The 1 in 3 probability isn't an error or an outlier. It's the result of precise measurements analyzed by the world's most sophisticated orbital mechanics software. Atlas might miss Earth, but it might not. And those odds are completely unacceptable for an object capable of causing mass extinction. The cascade of secure communications that follows this calculation represents diplomacy at its most urgent. Space agency directors contact defense ministers. Defense ministers contact heads of state. Emergency management officials begin dusting off contingency plans that were written as theoretical exercises but never expected to be implemented. The phrase extinction-level event begins appearing in classified briefings with disturbing frequency. The human responses to this mounting crisis reveal the full spectrum of psychological defense mechanisms. Some astronomers respond with hyperactive professionalism, taking measurements with obsessive precision as though perfect data might somehow change the fundamental physics. Others retreat into gallows humor, making jokes about updating their resumes to include prevented apocalypse or failed to prevent apocalypse as appropriate. A few simply continue working with the steady concentration of people who understand that panic is not a useful response to mathematical certainty. October 18th arrives, with Atlas now visible to dedicated amateur astronomers using telescopes with 8-inch mirrors. The comet has developed a faint coma, a cloud of vaporized ice surrounding its nucleus that makes it appear fuzzy against the background stars. This visible sign of the comet's approach adds psychological weight to the statistical threat. Atlas is no longer just numbers on computer screens. It's an object that people can see with their own eyes, growing brighter as it approaches. The decision about public disclosure becomes unavoidable. Government officials, space agency administrators, and crisis management experts engage in debates that would be fascinating if the stakes weren't quite so high. How do you inform 7 billion people that they might all be dead in 7 months without triggering mass panic, economic collapse, or the complete breakdown of social order? This proves to be a remarkably complex communication challenge. The arguments for immediate disclosure center on human rights and practical necessity. People deserve to know about threats to their existence, and any effective response to Atlas will require unprecedented international cooperation and resource mobilization. Keeping the threat secret would make meaningful preparation impossible and would represent a fundamental betrayal of democratic principles. The arguments for delayed disclosure focus on social stability and the need for preliminary response planning. Announcing a potential extinction event without simultaneous announcement of response strategies might trigger panic that kills more people than the actual impact. Better, some argue, to spend a few weeks developing preliminary deflection plans before informing the public that such plans might be necessary. The compromise, when it finally emerges, represents a masterpiece of political and scientific diplomacy. The announcement will acknowledge Atlas as a near-Earth object requiring enhanced monitoring and preliminary assessment of deflection options. This phrasing manages to convey the essential information while avoiding language that might trigger immediate social collapse. The announcement will be coordinated across multiple governments and space agencies to prevent conflicting messages and will be accompanied by statements about ongoing response planning. The final decision to proceed with public disclosure comes at 7:30 p.m. Eastern Time on October 18th. The secure conference call includes representatives from NASA, the European Space Agency, the Russian Space Program, the Chinese National Space Administration, and the United Nations Office for Outer Space Affairs. The conversation lasts 43 minutes and concludes with unanimous agreement that humanity deserves to know about the cosmic sword hanging over its collective head. The announcement itself, delivered simultaneously from Washington, Brussels, Moscow, Beijing, and Vienna at 11 p.m. Eastern Time, becomes an instant historical document. The careful language cannot disguise the fundamental message. A mountain-sized comet with a 1 in 3 chance of ending human civilization will arrive in 237 days. The response is immediate and predictable. Stock markets plummet, emergency hotlines are overwhelmed, and social media explodes with equal parts panic and denial. But perhaps the most remarkable response comes from an unexpected source. Within 12 hours of the announcement, offers of assistance begin pouring in from around the world. Amateur astronomers volunteer telescope time for continued observations. Engineering firms offer pro bono services for deflection mission planning. University physics departments redirect research toward impact prevention. Humanity's response to potential extinction reveals something profound about our species. When faced with cosmic threats, our instinct is not to despair, but to fight back. The 72 hours from Chen's initial discovery to the public announcement represent a unique moment in human history, the first time our species has confronted its potential extinction with full scientific understanding of both the threat and the remaining time to respond. The mathematics are clear, the timeline is fixed, and the stakes are absolute. Atlas continues its approach with the patient inevitability of orbital mechanics. Indifferent to human hopes and fears, in 237 days, we will discover whether mathematics, engineering, and human determination can overcome 4.5 billion years of cosmic coincidence. The countdown has begun, and failure is not an option our species can afford to consider. May 9th, 2025, 7:52 p.m. Eastern Time. Atlas enters Earth's atmosphere above the Pacific Ocean at 67 kilometers per second, 200 times faster than a rifle bullet, roughly the speed at which the planet itself orbits the Sun. What follows in the next 8 minutes represents the most violent natural event in human history, a demonstration of cosmic forces that makes every previous disaster seem like a gentle spring rain. The initial contact occurs at an altitude of 120 kilometers, in the rarefied upper atmosphere where the International Space Station normally orbits. At this height, air density is roughly 1/10,000,000th of sea level pressure, barely enough to register on most instruments. For Atlas, traveling at interplanetary velocities, even this whisper-thin atmosphere represents an immovable wall. The comet begins compressing the air in front of it to pressures and temperatures that defy comprehension. Within the first second, the compressed air reaches 20,000 degrees Celsius, hotter than the surface of the Sun. This isn't metaphorical heat. This is plasma formation, the creation of matter in a state that exists naturally only in stellar cores and nuclear explosions. From space, Atlas appears to ignite like a second star being born, visible from Earth's surface as a point of light brighter than Venus at midday. The physics of hypervelocity, atmospheric entry, operate on principles that seem almost deliberately destructive. Air molecules, normally invisible and weightless, become a crushing force when encountered at cosmic speeds. The comet's leading edge experiences pressures equivalent to being crushed under a stack of automobiles 20 stories high, while simultaneously being heated to temperatures that would vaporize titanium. The fact that Atlas survives this initial assault speaks to both its massive size and its dense composition. At 7:52 and 30 seconds, Atlas has descended to 80 kilometers altitude, entering the mesosphere, where meteors typically burn up completely. But meteors are typically the size of gravel or, at most, small boulders. Atlas is a mountain, and mountains do not burn up quietly. Instead, the comet begins shedding material like a cosmic blowtorch, leaving a trail of superheated debris that stretches across half the Pacific. The sonic boom generated by Atlas's passage defies easy description. Sound waves traveling at hypersonic velocities create pressures that shatter windows in aircraft flying 300 kilometers away. The boom is audible across the entire Pacific basin, a sound so deep and powerful that it registers on seismographs as far away as Alaska and Chile. Whales diving in the Mariana Trench detect the pressure waves and surface in apparent confusion, their echolocation systems overwhelmed by acoustic chaos. By 7:52 and 45 seconds, Atlas reaches 50 kilometers altitude, entering the stratosphere with roughly 60% of its original mass intact. The comet is now glowing white-hot, shedding molten rock and vaporized ice in a trail that illuminates the entire western Pacific. From the perspective of observers on the ground, those lucky enough to be looking in the right direction, Atlas appears as a second sun crossing the sky, bright enough to cast shadows at sunset. The final 15 seconds of Atlas's atmospheric journey represent physics at its most violent and unforgiving. The comet, now compressed and superheated by its passage through increasingly dense air, begins to fracture along stress lines created by thermal expansion. But unlike the controlled breakup that destroys smaller meteors, Atlas's fragmentation releases energy in discrete bursts, a series of explosions that register as nuclear-level detonations in the upper atmosphere. At 7:52 and 58 seconds, Atlas reaches 10 kilometers altitude, having shed roughly 40% of its mass to atmospheric friction and thermal stress. What remains? Approximately 1.3 kilometers of dense, superheated rock and ice traveling at 55 kilometers per second represents more concentrated kinetic energy than humanity has ever witnessed. The comet is no longer falling. It's punching through the atmosphere like a cosmic bullet aimed at the Pacific Ocean. The final 2 seconds unfold with the terrible precision of celestial mechanics. Atlas, now a glowing projectile roughly the size of a large city block, descends through the last 10 kilometers of atmosphere without significant deceleration. The air at this altitude is dense enough to create tremendous friction, but not dense enough to slow an object of such massive momentum traveling at such fantastic speed. The comet strikes the Pacific Ocean at 7:53 p.m. exactly, 217 miles west of Los Angeles. The impact itself represents a collision between cosmic and terrestrial forces that produces effects beyond normal human experience. Atlas strikes the ocean with the kinetic energy of 10 million megatons, 700,000 times the energy of the bomb that destroyed Hiroshima. But this comparison, while mathematically accurate, fails to capture the true scale of destruction. Nuclear weapons release their energy as heat and radiation. Kinetic impacts concentrate their energy into mechanical force that physically reshapes the planet's surface. The ocean doesn't splash when Atlas hits it. Water, when struck by an object traveling at 55 kilometers per second, behaves more like concrete than liquid. The impact creates a cavity 17 miles deep, a temporary hole in the Pacific that exposes the seafloor and displaces roughly 1 trillion tons of water in the first millisecond. The cavity forms so rapidly that water cannot flow back to fill it, creating a vacuum that exists for several seconds, before the laws of physics reassert themselves with catastrophic force. The shockwave from the impact travels outward through the ocean at 5 times the speed of sound, creating pressures that crush everything in its path. Deep-sea creatures adapted to the crushing depths of the ocean trenches are pulverized by pressure waves that exceed anything in their evolutionary experience. The Pacific Plate itself rings like a struck bell, transmitting seismic waves that register magnitude 9.7 on earthquake monitoring stations worldwide. But the tsunami that follows the impact represents the true measure of Atlas's destructive power. As water rushes back to fill the impact cavity, it creates a wave 800 feet high, taller than the Golden Gate Bridge, that radiates outward from the impact point at 600 miles per hour. This isn't the gradually building swell of an ordinary tsunami. This is a wall of water moving at nearly the speed of sound, carrying enough kinetic energy to level mountains. The wave reaches the California coast in 43 minutes. From the perspective of observers on shore, those who remain after the initial panic and evacuation attempts, the horizon simply disappears, replaced by a growing wall of dark water that blots out the setting sun. The tsunami doesn't break like an ocean wave. It simply rises, carrying with it the accumulated debris of the Pacific Ocean floor and everything it has encountered during its eastward journey. Los Angeles vanishes first, the 800-foot wave sweeping inland for 30 miles, carrying away buildings, vehicles, and 27 million lives with the casual indifference of natural forces operating at geological scales. San Francisco Bay becomes a funnel that concentrates the wave's energy, driving water over the coastal mountains and into the Central Valley. Seattle, Portland, and every coastal city from Baja California to British Columbia disappear beneath water that moves with the force of continents colliding. But the immediate destruction, catastrophic as it is, represents only the beginning of Atlas's assault on Earth's biosphere. The impact has ejected 40 trillion tons of pulverized rock, vaporized water, and superheated gases into the atmosphere. This debris cloud, propelled by the explosion's shockwave, rises through the stratosphere and into the mesosphere, where it begins to spread around the globe like a shroud, Within 6 hours, the debris cloud has circled the planet, blocking sunlight and beginning the process that will define the next 7 years of Earth's climate. The suspended particles reflect and absorb solar radiation, causing surface temperatures to plummet 40 degrees Celsius within 2 weeks. This isn't gradual cooling. This is the rapid onset of impact winter, a phenomenon that makes ice ages look like minor seasonal variations. The collapse of photosynthesis begins almost immediately. Plants, deprived of sunlight, begin dying within days. Phytoplankton, the microscopic marine organisms that form the base of oceanic food chains, cannot survive in the darkened, debris-laden seas. The global food web, built over billions of years of evolutionary fine-tuning, unravels from bottom to top with the efficiency of a biological collapse. From orbit, the International Space Station provides a unique perspective on Earth's transformation. The astronauts aboard, those fortunate enough to have been above the atmosphere when Atlas struck, document the planet's evolution from blue marble to shrouded sphere. The radio communications with ground control, increasingly sporadic as communication networks fail, provide humanity's last coherent record of the impact's immediate aftermath, the electromagnetic pulse generated by Atlas's passage through the upper atmosphere destroys most satellite networks within hours of impact. Navigation systems fail, communication networks go dark, and the technological infrastructure that supports modern civilization simply stops functioning. The world doesn't end with nuclear war or plague. It ends with a mountain from space that turns off the lights and destroys the systems that keep 7 billion people alive. In the American Midwest, far from the Pacific devastation, people watch the western sky turn orange as atmospheric debris creates the most spectacular sunset in human history. Within days, these same people will be struggling to survive in a world where crops cannot grow, where transportation systems have collapsed, and where the sun itself has become a dim memory behind layers of cosmic dust the geological record will preserve. Atlas's impact as a thin layer of shocked quartz and iridium, the same signature, left by the asteroid that ended the age of dinosaurs 65 million years ago. But unlike that ancient catastrophe, Atlas's impact occurs in the age of human civilization, creating an archaeological boundary that will mark the end of one chapter in Earth's history and the beginning of another. From space, Earth still appears beautiful, a blue and white sphere spinning peacefully in the cosmic dark. But the white is no longer clouds and ice caps. It's the debris cloud that will darken Earth's skies for years to come. The blue oceans, when visible through breaks in the shroud, show the scars of tsunami destruction along every coastline. The planet that gave birth to human civilization has been transformed by 8 minutes of cosmic violence into something alien and hostile. Yet even in this darkness, life persists. In the depths of the ocean, around hydrothermal vents powered by Earth's internal heat, organisms continue their ancient biological processes. In caves and underground rivers, ecosystems that never depended on sunlight continue unchanged. In the frozen soil of the Arctic, seeds and spores wait for conditions that may not return for decades. Atlas has ended the world as humans knew it, but it has not ended the world itself. What emerges from the impact winter will depend on the resilience of life, the ingenuity of any human survivors, and the patient processes of geological and biological recovery that operate on timescales far longer than individual human lives. The cosmic dice have been thrown, and the result is 8 minutes of violence that will echo through Earth's history for millions of years to come. November 1st, 2024. Humanity has exactly 219 days remaining before potential extinction. In a converted aircraft hangar in Houston, the world's most brilliant minds gather for what may be the most important meeting in human history. The Planetary Defense Task Force represents humanity's desperate attempt to do something that has never been done before. deliberately alter the trajectory of a mountain-sized object traveling at cosmic velocities across interplanetary distances. The assembly reads like a fantasy draft of human intellectual achievement. Nobel laureates in physics sit beside oil rig engineers who understand how to move massive objects under impossible conditions. Rocket scientists debate launch windows with demolition experts who know how explosives behave in vacuum. Nuclear weapons designers collaborate with software engineers who model orbital mechanics. The diversity of expertise reflects a simple truth. Preventing extinction requires every type of human knowledge working in perfect coordination. Dr. Elena Rodriguez, hastily appointed as the task force coordinator, faces a challenge that no management training could prepare her for, organizing humanity's response to cosmic catastrophe while the clock counts down to potential extinction. Her first briefing to the assembled experts contains perhaps the most sobering PowerPoint presentation ever created. 219 days to design, build, launch, and execute a mission to deflect an object that masses roughly 7 billion tons and moves faster than anything humans have ever attempted to intercept. The nuclear option dominates initial discussions, though not for the reasons Hollywood might suggest. Popular fiction portrays comet deflection as a matter of drilling to the center and detonating. A single massive warhead, a scenario that real physicists describe with the kind of polite professional language that translates roughly to absolutely insane. Atlas isn't a loosely bound pile of gravel that can be blown apart. It's a solid mass of rock and ice that has survived 4.5 billion years in space. Fragmenting it would simply transform one extinction-level impact into several slightly smaller extinction-level impacts. Instead, the nuclear strategy involves what physicists call stand-off detonation, exploding nuclear devices near Atlas's surface rather than inside it. The concept relies on the peculiar physics of nuclear weapons in vacuum, where the absence of atmosphere prevents the formation of destructive blast waves. In space, nuclear explosions release their energy primarily as intense radiation, which can vaporize surface material and create thrust through the rocket principle. The mathematics are simultaneously elegant and terrifying. 41 megaton warheads, detonated in precise sequence 200 meters from Atlas's surface, would vaporize roughly 1 million tons of surface material. This vaporized matter, expanding into space at several kilometers per second, would act like an enormous rocket engine, gradually pushing the comet away from its collision course with Earth. The required velocity change, just 17 meters per second, applied at the right time and place, seems almost laughably small until you realize it must be. Imparted to an object with the mass of Mount Everest, the engineering challenges of nuclear deflection push human technology to its absolute limits. The warheads must be delivered with precision that makes landing on the moon look straightforward. Atlas will be roughly 40 million kilometers from Earth at intercept, a distance that light takes over 2 minutes to cross. Radio signals controlling the detonation sequence face communication delays that require the weapons to operate autonomously, following pre-programmed instructions with no possibility of real-time human intervention. Dr. Sarah Kim, the mission's nuclear systems engineer, presents calculations that make the room fall silent. To reach Atlas in time, launch must occur no later than December 15th, giving her team exactly 44 days to design, build, test and deploy 40 nuclear weapons capable of operating in deep space for 5 months. This timeline represents the kind of engineering miracle that normally takes decades to achieve, compressed into 6 weeks because failure means extinction. But nuclear deflection isn't the only option under consideration. The gravity tractor concept offers an elegant alternative that relies on gravitational attraction rather than explosive force. The idea involves parking a massive spacecraft near Atlas and allowing gravitational attraction to gradually pull the comet off course. The physics are gentle, predictable, and completely inadequate for the timeline involved. Calculations show that a 10,000-ton spacecraft, roughly the mass of a naval destroyer, would require 17 years to produce the necessary course correction. Humanity has 7 months. Solar sail deflection represents perhaps the most beautiful concept under consideration. Enormous reflective surfaces, each covering hundreds of square kilometers, would unfurl near Atlas like cosmic flowers. Solar radiation pressure, normally negligible, becomes significant when applied across such vast areas. The sails would act like mirrors, reflecting sunlight and using photon momentum to gradually push the comet away from Earth. The concept is elegant, theoretically sound, and practically impossible to deploy in the available time frame. The kinetic impactor strategy takes a more direct approach. Hit Atlas with massive projectiles traveling at high velocity and hope the momentum transfer changes its trajectory. This represents perhaps the most intuitive deflection method. If something is heading toward you, throw something at it to knock it off course. The challenge lies in the scale required. Computer simulations suggest that deflecting Atlas would require 50 impactors, each massing several tons and traveling at 20 kilometers per second. Current inventory of suitable launch vehicles, 3. As December approaches with terrifying speed, the task force settles on humanity's most desperate gambit, a combined approach that throws every available technology at the problem simultaneously. The mission architecture reads like science fiction written by committee. 23 nuclear devices will provide the primary deflection force. 4 kinetic impactors will supplement the nuclear thrust. History's largest solar sail, covering an area the size of Rhode Island, will deploy near Atlas to provide continuous but gentle pressure over the remaining months before impact. The international coordination required for this mission defies every precedent in human cooperation. Nations that have been enemies for generations suddenly share their most classified technologies. North Korea offers its entire nuclear arsenal for the mission, along with launch vehicles previously reserved for intercontinental ballistic missiles. Russia provides heavy-lift rockets originally designed to carry Soviet lunar missions. China contributes its most advanced guidance systems, technologies normally guarded as state secrets. The United States commits its remaining space shuttle fleet, vehicles scheduled for retirement but pressed back into emergency service. Europe offers the precision manufacturing capabilities needed to build solar sail components larger than anything previously constructed. India provides the software expertise needed to coordinate autonomous operations across interplanetary distances. Even nations without space programs contribute. Switzerland offers precision timing equipment, Germany provides advanced metallurgy, and Japan contributes the electronics that must function reliably in the radiation environment of deep space. The human stories behind this technological mobilization reveal both the best and most desperate aspects of human nature. Dr. Kim hasn't seen her family in 6 weeks. Sleeping under her desk while designing nuclear systems that must work perfectly on the first attempt. Rajesh Patel, the Indian software engineer coordinating the mission's guidance systems, codes continuously while delirious with flu, sustained by coffee and the knowledge that debugging errors after launch isn't an option. The breakthrough that makes the entire mission possible comes from an unexpected source. Miguel Santos, the janitor at the Houston facility who witnessed Chen's original discovery, makes a casual comment during one of his late-night cleaning rounds. Observing the engineers struggling with solar sail deployment mechanisms, he suggests why not just paint one side white and the other black like those spinning things at science museums. The comment leads to the albedo modification concept, using differential heating to create asymmetric outgassing that acts like natural rocket thrust. The engineering teams realize that they don't need to deploy separate solar sails. They can modify Atlas itself. Nuclear detonations will not only provide direct thrust, but will also alter the comet's surface reflectivity by creating patterns of light and dark areas. They can harness Atlas's own outgassing to provide continuous course correction throughout its remaining approach to Earth. It's elegant, it's unprecedented, and it's humanity's best hope for survival. Launch day arrives with military precision and scientific desperation. December 15th, 2024, becomes the most important date in human history as rockets lift off from launch pads around the world in a coordinated sequence that has never been attempted. The largest international space mission ever undertaken launches across 36 hours. With backup launches scheduled in case of failures, the first wave consists of kinetic impactors, solid tungsten projectiles launched on hyperbolic trajectories that will intersect Atlas's orbit in March 2025. These serve as pathfinders, testing tracking and navigation systems while providing preliminary momentum transfer. Their success or failure will determine whether the more complex nuclear phase can proceed with confidence. The nuclear delivery vehicles launch second, carrying their 1 megaton payloads on precisely calculated trajectories. Each weapon operates independently, with its own navigation system, proximity sensors, and detonation controls. They will coast for 5 months through interplanetary space, their electronics gradually degrading from cosmic radiation, racing against time and component failure. To reach their target, the final launch carries the solar sail deployment system, kilometers of reflective fabric that must unfurl perfectly in the vacuum of space near Atlas. This represents the mission's longest-term component, designed to provide continuous, gentle pressure even after the nuclear phase concludes. If everything works perfectly, the sail will operate for months, gradually nudging Atlas away from its appointment with Earth. Mission success probability, calculated by the world's most advanced computer models, reaches 37%. These odds represent the combined likelihood of successful launch, accurate navigation across interplanetary distances, precise timing of nuclear detonations, and sufficient deflection to alter Atlas's trajectory by the required 17 meters per second. 37% represents humanity's best effort against cosmic forces that have operated unchanged for billions of years. The waiting begins immediately after launch. For the next 5 months, humanity can only watch as its technological emissaries coast through the darkness toward a rendezvous with extinction. Ground control monitors the spacecraft through radio signals that take increasingly longer to arrive as the distance grows. By February, communications require 20-minute round trips, transforming mission control from active guidance to passive observation. The mission represents more than technology. It represents philosophy. For the first time in human history, our species has attempted to consciously alter the trajectory of cosmic events, rather than simply enduring whatever the universe provides. The mission succeeds or fails based on human understanding of physics, engineering precision, and the hope that intelligence can overcome the blind mechanical forces that have shaped Earth's history for 4 billion years. As Atlas continues its approach through the winter and spring of 2025, every human being on Earth shares the same countdown. Success means continuation of human civilization. Failure means joining the dinosaurs in the fossil record. The mission's 37% success probability represents the mathematical expression of hope itself, the calculated chance that intelligence, cooperation, and determination can triumph over cosmic indifference. In exactly 146 days, humanity will discover whether our species possesses the technological capability to consciously direct its own evolutionary future, or whether we remain subject to the same cosmic lottery that has determined the fate of every other species in Earth's history. The dice are in the air, traveling at interplanetary velocities, and the outcome will determine whether human civilization has a future worth calculating. Deep beneath the Pacific Ocean, where tectonic plates spread apart in the perpetual darkness 3 miles below the surface, Water reaches 400 degrees Celsius, yet refuses to boil. The crushing pressure at these depths, roughly equivalent to having the entire weight of the atmosphere pressing down 300 times over, keeps the superheated water in liquid form. Here, in conditions that would instantly kill any surface-dwelling organism, life not only survives, but thrives with an abundance that rivals tropical rainforests. These hydrothermal vents, powered by Earth's internal heat rather than solar energy, represent one of the planet's most remarkable ecosystems. Giant tube worms, some reaching lengths of 8 feet, wave gently in the mineral-rich currents like alien flowers. Their blood contains specialized hemoglobin that filters nutrients from water so toxic it would dissolve most metals. These creatures have no digestive systems. Instead, they host colonies of chemosynthetic bacteria that convert hydrogen sulfide, deadly poison to surface life, into the energy needed for survival. The beauty of these deep-sea communities lies in their complete independence from the surface world. Atlas could darken the skies for decades, freeze the oceans solid, and sterilize every continent, and the tube worms would continue their ancient dance with their bacterial partners, blissfully unaware that an apocalypse had occurred 3 miles above their heads. They represent life's ultimate insurance policy against cosmic catastrophe. Ecosystems that operate on entirely different principles than the sun-dependent biosphere that supports human civilization, but these deep-sea oases aren't the only refuges where life might weather Atlas's impact. Scattered across the planet like hidden treasure chests, pockets of extremophile organisms have established footholds in places that seem more suited to science fiction than biology. In South Africa's gold mines, bacteria live 2 miles underground, drawing energy from the radioactive decay of uranium in the surrounding rock. These organisms have been isolated from the surface world for millions of years, creating their own closed ecosystems that operate on geological timescales. The Witwatersrand Basin, where these subterranean communities flourish, contains what may be Earth's deepest biosphere. The bacteria here don't photosynthesize or depend on organic matter falling from above. They literally eat rock, breaking down sulfur compounds and using the released energy to power their cellular machinery. Their metabolism operates so slowly that individual bacterial generations may span decades, but their patience is rewarded with immortality. These communities could continue unchanged for millions of years after Atlas turns the surface world into a frozen wasteland. In the permafrost of Siberia, another form of biological time travel awaits resurrection. Cores drilled through permanently frozen soil reveal bacterial spores that have remained viable for over 500,000 years, preserved in crystalline ice like microscopic sleeping beauties. These organisms represent life's ability to essentially pause itself, entering a state of suspended animation so profound that cellular processes virtually stop. When conditions improve, even hundreds of thousands of years later, they simply resume living as though no time has passed. The implications for post-Atlas survival are profound. Even if the impact winter lasts decades, even if surface temperatures remain below freezing for generations, these dormant life forms would patiently wait for the sun's return. They've survived ice ages, volcanic winters, and mass extinctions before. Atlas would represent just another temporary inconvenience in their geological timescale existence. Perhaps the most visually striking example of life's ingenuity appears in Antarctica's Blood Falls, where iron-oxidizing microbes create spectacular crimson streams flowing from beneath Taylor Glacier. These organisms have been trapped under ice for over 1 million years, yet they continue to thrive in water so salty it cannot freeze even at -10 degrees Celsius. They've evolved to use iron as their electron acceptor, essentially breathing rust instead of oxygen, creating metabolic pathways that seem almost deliberately designed to survive in post-apocalyptic conditions. To understand how life might recover from Atlas's impact, we need to examine Earth's previous near-death experiences. The planet has survived at least 5 major mass extinctions, each one eliminating the majority of existing species, yet somehow setting the stage for explosive evolutionary recovery. The patterns written in stone and DNA suggest that life doesn't just survive catastrophe, it uses catastrophe as an opportunity for reinvention. 2.4 billion years ago, cyanobacteria fundamentally poisoned Earth's atmosphere by releasing oxygen as a waste product of photosynthesis. This great oxidation event killed most existing life forms, which had evolved in an oxygen-free world and found the new atmosphere toxic. Yet this mass extinction paved the way for aerobic respiration and eventually complex multicellular life. What seemed like planetary catastrophe became the foundation for every organism that breathes oxygen today, including humans. The Permian extinction, occurring 251 million years ago, represents the closest Earth has ever come to complete sterilization. Massive volcanic eruptions in Siberia released enough greenhouse gases to raise global temperatures by 10 degrees Celsius, while simultaneously acidifying the oceans and depleting atmospheric oxygen. 96% of marine species and 70% of terrestrial species vanished from the fossil record. Yet life's response to this near-total catastrophe demonstrates remarkable resilience. The 4% of species that survived the Permian extinction didn't just gradually repopulate the planet. They exploded into new evolutionary forms with unprecedented diversity. Within 10 million years, an eye blink in geological time, Earth's ecosystems had not only recovered, but had evolved entirely new types of organisms. The age of reptiles, and eventually the age of mammals, emerged directly from the ashes of the Permian catastrophe. The most relevant precedent for Atlas's potential impact occurred 65 million years ago, when the Chicxulub impactor ended the Mesozoic era with brutal efficiency. This asteroid, roughly 10 kilometers in diameter, struck Earth with energy equivalent to 5 billion atomic bombs. The impact triggered massive wildfires, created acid rain that sterilized entire continents, and shrouded the planet in darkness for months. The dinosaurs, after ruling Earth for 165 million years, vanished within geological moments. Yet their extinction opened ecological niches that allowed tiny mammals, previously relegated to nocturnal scavenging, to inherit the planet. Within 10 million years, mammals had diversified into forms ranging from whale ancestors to early primates. The impact that ended the age of dinosaurs ultimately made possible the age of mammals and, eventually, the emergence of human intelligence. The recovery patterns following these ancient catastrophes suggest a predictable sequence of biological renewal. First, the impact winter breaks as atmospheric debris settles and normal precipitation returns. This process, while seeming interminable to any surviving humans, typically requires only a few years from the perspective of geological time. In the oceans, photosynthetic plankton would stage the first comeback. These microscopic organisms produce spores capable of surviving in sediments for decades, waiting for the return of sunlight. When the skies finally clear, these dormant seeds of oceanic life would bloom in explosive abundance, their populations unconstrained by the predators and competitors that Atlas eliminated. The resulting plankton blooms would be visible from space, turning vast areas of ocean green with photosynthetic activity. On land, ferns would likely lead the botanical recovery, just as they did after the Chicxulub impact. Fern spores are among the most resilient propagules in the plant kingdom, capable of surviving extreme temperature fluctuations, desiccation, and radiation exposure. The post-impact landscape would initially be carpeted with ferns, creating a green world that might look alien to human eyes, but would represent the first step toward ecosystem recovery. The seed banks scattered across the planet represent one of humanity's most far-sighted contributions to post-catastrophe recovery. The Svalbard Global Seed Vault, built into a mountainside in Arctic Norway, contains over 2.5 billion seeds from 900,000 crop varieties. Designed to survive even nuclear war, these genetic time capsules could provide the biological foundation for agricultural recovery decades or centuries after Atlas. But Svalbard represents just one node in a global network of seed preservation. The Kew Gardens Millennium Seed Bank in England contains seeds from 40,000 plant species. Similar facilities in Australia, the United States, Russia and China preserve genetic diversity that could prove invaluable for ecosystem reconstruction. Even if human civilization collapses completely, these repositories would remain viable for centuries, waiting for intelligence, whether human or otherwise, to rediscover and deploy them. The timeline for ecosystem recovery follows patterns established over billions of years of evolution. Within decades of Atlas's impact, microbial communities would re-establish themselves around geothermal features and in protected environments. Within centuries, pioneer plant species would begin recolonizing the landscape, their growth accelerated by the lack of competition from established ecosystems. Complex ecosystems might require millennia to fully develop, but the building blocks would appear much sooner. Small mammals, birds and insects surviving in underground refugia or protected environments would emerge to find a world of empty ecological niches. Evolution would respond to these opportunities with the kind of rapid diversification seen after previous mass extinctions. The ocean recovery would likely proceed faster than terrestrial rehabilitation. Marine ecosystems, while devastated by Atlas's initial impact and the subsequent climate chaos, retain deep-water refugia that would serve as sources for recolonization. Deep-sea fish populations, largely unaffected by surface catastrophe, would gradually expand their ranges as ocean chemistry returns to normal. Perhaps most remarkably, some regions might emerge from Atlas's impact in better condition than before. Volcanic areas, where geothermal activity provides local heat sources, could become oases of biological activity even during the worst of the impact winter. Yellowstone, Iceland, the geysers of Kamchatka. These regions might serve as arcs of biodiversity, preserving complex ecosystems throughout the global catastrophe. The recovery wouldn't produce a duplicate of pre-impact Earth. Evolution doesn't repeat itself. It explores new possibilities. The planet that emerges from Atlas's impact winter might host ecosystems unlike anything in Earth's history. New symbioses, novel metabolic pathways, and unprecedented ecological relationships would develop as life adapts to post-catastrophe conditions. From the perspective of deep time, Atlas's impact would represent just another of Earth's periodic renewals. The planet has endured bombardment by asteroids, massive volcanic eruptions, ice ages, and atmospheric transformations that would seem apocalyptic to human observers. Yet each catastrophe has ultimately led to new forms of life, new ecosystems, and new possibilities for biological complexity. The microbes in Earth's deepest rocks, the spores sleeping in Arctic permafrost, the seeds locked in mountain vaults, these represent life's patient confidence in its own future. They've survived every catastrophe Earth can produce, and they'll survive Atlas too. The question isn't whether life will recover from humanity's potential extinction event, but what new forms that recovery might take. In the grand story of terrestrial biology, even the worst-case scenario for human civilization represents just another chapter in life's ongoing experiment with complexity, consciousness, and cosmic survival. Life has been finding ways to persist for nearly 4 billion years, and it's not about to stop now, regardless of what the universe throws at it. May 10, 2025. The deflection mission has failed. Not completely. The nuclear detonations shifted Atlas's path by 412 kilometers, a distance that represents humanity's first successful attempt at planetary defense. But 412 kilometers, while impressive by human standards, falls short of the 5,000 kilometers needed to ensure a complete miss. The comet that should have struck downtown Los Angeles instead impacts the Pacific Ocean 200 miles offshore. 37% success becomes 100% mitigation. 27 million people live who would otherwise have died. This distinction between total success and partial victory becomes the defining characteristic of humanity's first encounter with extinction-level cosmic threats. We didn't stop Atlas, but we proved that stopping Atlas was possible. The mission succeeded well enough to transform global catastrophe into regional disaster, complete extinction into traumatic survival. In the grand mathematics of cosmic threats, this partial victory represents a revolution in human capability as significant as the invention of agriculture or the discovery of fire. The immediate aftermath reveals both the scope of the catastrophe and the limits of human preparation. The Pacific impact destroys coastal cities from California to Chile, but leaves the continental interiors largely intact. The resulting tsunami devastates island nations and coastal populations, but humanity's inland cities survive to witness the impact winter. Agricultural collapse kills hundreds of millions, but not billions. Nuclear power plants, hardened against electromagnetic pulses and operated by skeleton crews, continue generating electricity through the darkest months of climate disruption. Most remarkably, the international cooperation forged during the deflection mission doesn't dissolve with Atlas's impact. The shared experience of near extinction creates bonds between nations that transcend traditional geopolitical boundaries. The Emergency Coordination Protocol, hastily assembled during humanity's darkest hours, becomes the foundation for a new form of global governance designed around the simple principle that cosmic threats require species-level responses. Within 18 months of Atlas's impact, the United Nations creates the Global Defense Directorate with a budget that exceeds the combined military spending of all nations before the crisis. This isn't the gradual bureaucratic expansion typical of international organizations. This is the conscious decision by human civilization to prioritize species survival above national interests. Every radio telescope on Earth, every optical observatory, every radar installation capable of tracking distant objects becomes part of a coordinated early warning network. The Deep Space Early Warning Array represents humanity's most ambitious response to the Atlas crisis. By 2030, a constellation of 64 automated Sentinel stations orbits the Sun at Jupiter's distance, their sensors continuously scanning for objects that might threaten Earth. These stations, each roughly the size of a small building and powered by radioisotope generators, represent our species' commitment to never again being surprised by cosmic threats. The technological requirements for this early warning system push human space capabilities far beyond anything achieved during the pre-Atlas era. Each Sentinel station must operate autonomously for decades in the radiation-rich environment beyond Mars, communicating across astronomical distances while maintaining sensor accuracy sufficient to detect kilometer-sized objects at ranges exceeding 1 billion kilometers. The engineering challenges make landing humans on the Moon look like a casual weekend project. But perhaps the most profound change occurs in human consciousness itself. The generation that lived through Atlas Spring, those 237 days between discovery and impact, thinks differently about Earth, sky, and humanity's place in the cosmic order. School children learn orbital mechanics alongside basic arithmetic, not as abstract academic exercise, but as essential knowledge for species survival. Every major city constructs deep shelters designed not for nuclear war, but for impact winter. The phrase planetary backup enters common usage as space colonization accelerates from distant dream to immediate necessity. The first permanent lunar base, officially named Chen Station in honor of the astronomer who spotted Atlas, breaks ground in 2028. Unlike the brief sorties of Apollo astronauts, Chen Station represents genuine human settlement beyond Earth, a self-sustaining community of scientists, engineers, and support personnel who live, work, and raise children in the low-gravity environment of the Moon. The base's primary mission centers on housing the telescopes that will spot the next Atlas, while there's still time for deflection. Rather than damage control, the Lunar Observatory Complex at Chen Station represents optical engineering at its most ambitious. The primary telescope mirror, constructed from lunar materials to avoid the costs of launching massive components from Earth's gravity well, measures 40 meters in diameter, 4 times larger than any Earth-based instrument. This mirror, ground and polished by robotic systems in the Moon's vacuum environment, can detect objects as small as 50 meters in diameter at distances of several astronomical units. But Chen Station's importance transcends astronomy. The lunar colony proves that humans can establish self-sustaining communities beyond Earth, creating what planetary defense experts call civilizational redundancy. If a future impact succeeds where Atlas failed, Chen Station would preserve human knowledge, culture, and genetic diversity, while Earth recovered from whatever catastrophe might befall the home planet. By 2035, 10,000 humans live permanently beyond Earth's atmosphere. Chen Station has expanded into a complex of interconnected domes, housing universities, hospitals, manufacturing facilities, and even entertainment districts. Similar bases dot the lunar surface. New Geneva in the South Polar region specializes in ice mining and life support systems. Tsiolkovsky Station on the lunar far side hosts radio telescopes shielded from Earth's electronic interference. Armstrong Base near the equator serves as the primary launch point for missions to Mars and the asteroid belt. The Martian colonies, initially conceived as scientific outposts, transform into humanity's second major foothold in the solar system. New Sydney, constructed in the Chryse Planitia using modified lunar-based technology, houses 1,500 permanent residents by 2032. Unlike the lunar settlements, which depend on Earth for complex manufactured goods, the Martian colonies aim for complete self-sufficiency. The red planet's atmosphere, while thin and toxic, contains carbon dioxide that can be converted to oxygen and fuel. Its polar ice caps provide water. Its iron-rich soil supplies raw materials for construction and manufacturing. The expansion to Mars reveals something profound about human adaptability and determination. The generation that grows up in Martian gravity develops differently than Earth-born humans, taller, with enhanced lung capacity and modified bone density. These physiological adaptations, initially concerning to medical researchers, prove beneficial for life in reduced gravity environments. Within 2 generations, distinct populations of Martians and Lunarians begin developing cultural differences that reflect their unique environments. By 2040, over 1 million humans live permanently beyond Earth. This number represents more than mere colonization. It represents the conscious distribution of human civilization across multiple worlds to ensure species survival. The colonies aren't just outposts. They're comprehensive civilizations with their own universities, research institutions, cultural centers, and governance systems. Earth remains humanity's home, but it's no longer humanity's only home. The asteroid mining operations that supply these colonies create the first truly space-based economy. Robotic mining platforms stationed at Ceres, Vesta, and dozens of smaller asteroids extract metals, water, and rare Earth elements that make interplanetary settlement economically viable. A single metallic asteroid contains more platinum than has ever been mined on Earth, more iron than humanity has used throughout its entire industrial history. These mining operations also serve dual purposes as planetary defense assets. The same spacecraft designed to extract resources from asteroids can redirect threatening objects away from Earth. The infrastructure built for economic purposes becomes the foundation for comprehensive planetary protection. By 2045, humanity possesses the capability to deflect any reasonably sized cosmic threat with months or years of advance warning. The cultural impact of Atlas extends far beyond technology and space colonization. The shared experience of potential extinction creates what sociologists call species consciousness, a recognition that human survival depends on collective action rather than tribal competition. National borders don't disappear, but they become less relevant when faced with threats that could eliminate all nations. Simultaneously, religious and philosophical movements emerge around the concept of cosmic responsibility, the idea that intelligence in the universe carries an obligation to preserve and expand consciousness against the indifferent forces of nature. These movements, while diverse in their specific beliefs, share the common recognition that human survival isn't guaranteed by any cosmic principle, but must be actively maintained through knowledge, technology, and cooperation. The scientific revolution triggered by Atlas accelerates human understanding of physics, astronomy, and planetary science by decades. Research priorities shift toward practical applications of theoretical knowledge: how to detect cosmic threats, how to predict their behavior, how to deflect them, how to survive their impacts. The abstract becomes applied, the theoretical becomes essential, and the ivory tower becomes mission control for species survival. Perhaps most remarkably, the Atlas crisis reveals something unexpected about human nature. Our species responds to existential threats not with despair, but with determination. The same cognitive abilities that create art, music, and literature also create early warning systems, deflection missions, and backup civilizations on other worlds. The creativity that produces poetry also produces solutions to problems that have never existed before. The economic transformation proves equally profound. Industries that existed as curiosities before Atlas, space tourism, asteroid mining, extraterrestrial agriculture, become essential components of human civilization. Universities establish degree programs in planetary defense, off-world engineering, and interplanetary law. Children dream of careers in cosmic threat assessment and multi-world logistics rather than traditional earthbound professions. By 2050, a generation has grown up for whom space colonies, asteroid mines, and planetary defense systems represent normal features of human civilization rather than science fiction fantasies. For these post-Atlas humans, the idea that their species once lived exclusively on a single planet seems quaint and dangerously naive, like learning that their ancestors once lived in houses without fire departments or police. The transformation isn't without costs. The resources devoted to planetary defense and space colonization come at the expense of other human endeavors. Art, music, and literature survive, but receive less funding than engineering and applied physics. Social problems persist on Earth while humanity spreads across the solar system. The focus on species survival sometimes overshadows individual human welfare in ways that create new forms of inequality and social tension, yet even critics of the post-Atlas world acknowledge its fundamental achievement. Humanity has consciously taken control of its evolutionary future. For the first time in the history of terrestrial life, intelligence has become the dominant factor in determining species survival. Humans no longer wait passively for whatever cosmic catastrophe might eliminate them. They actively work to prevent such catastrophes while simultaneously preparing to survive them. The transformation culminates in 2060 with the launch of humanity's first interstellar probe. The Breakthrough Starshot 2 mission, powered by nuclear pulse propulsion and equipped with artificial intelligence systems, aims to establish humanity's first presence beyond the solar system. The probe carries digital archives of human knowledge, genetic templates for reconstructing terrestrial life, and instructions for building human civilization from basic materials. This mission represents more than exploration. It represents the conscious decision to ensure that human intelligence spreads across the galaxy, regardless of what happens to Earth or even to the solar system. The probe serves as a seed of consciousness, designed to grow into full human civilization around distant stars. If successful, it will mark the transformation of humanity from a planetary species to a galactic one. Atlas didn't destroy human civilization. It forced human civilization to grow up. The comet that should have ended our story instead became the catalyst for our expansion beyond every limit that had previously constrained us. We learned to look up not in wonder but in watchfulness. We learned to think not in terms of nations but in terms of species. We learned to plan not for decades but for millennia. The dinosaurs ruled Earth for 165 million years and never looked up at the sky with understanding. They never built telescopes, never calculated orbits, never conceived of deflecting cosmic threats. They dominated their planet completely and remained utterly vulnerable to forces beyond their comprehension. Humans had 300,000 years to develop similar capabilities and almost made the same mistake. Atlas arrived just in time to teach our species the most important lesson in the history of terrestrial intelligence, awareness, preparation, and the willingness to take conscious control of evolutionary processes represent the difference between cosmic victim and cosmic survivor. The universe remains vast, dangerous, and largely indifferent to human existence. But humanity is no longer small, helpless, or ignorant of cosmic threats. We have become something new in the history of Earth, a species that doesn't just adapt to environmental challenges but actively reshapes its environment, including the cosmic environment, to ensure its continued survival and expansion. Atlas taught us that extinction is optional, but only if we remain vigilant, cooperative, and committed to the long-term survival of intelligence in an otherwise unconscious universe. The lesson has been learned. The infrastructure has been built. The backup civilizations are thriving. The next mountain from space that heads toward Earth will find humanity ready for it.